Hello friends, this is part of the Miller, Ranch-Baran, Belitsky, and Deaver production company. This feature is where quality and education meet and the enrichment of your life begins.
Okay, I'm going to start talking about dynamic polymer melt testing. Yesterday, I finished capillary rheometry, and today subject is rotational rheometry or dynamic polymer melt testing. So I would like to mention that in general what you are going to do regarding your lab report, this is related to your fourth lab report. So your fourth lab report is melt indexer, capillary rheometry, and rotational rheometry that I'm going to cover today. So whatever you learn from those experiments, you are going to put in your lab report, and in the new situation, because of the lab are canceled, so you don't have any data, so I don't need any data to put in your lab report, so you just provide whatever you learn from the experiment, from the subject. Like whatever you are learning from the melt indexer and your data or capillary data that you already have. Some of you do, but some students don't have any data from capillary. So I'm rotationally also, you will learn some subject from today's lecture, and I will provide you more topic and video, from the subject. So what is rotational rheometry? With rotational rheometry, we measure shear stress and viscosity. The same concept that we use in capillary rheometry. I will explain later, what is the difference between capillary rheometry and rotational rheometry. But in general, you are dealing with velocity here. You are dealing with rotation. So, and as you can see, this is the concept of the rotational rheometry. You have a sample here, you have a disc. So this type of viscometry or rheometry are dealing with shear stress, with the shear rate, and there are different type of rheometry that I will explain later. So they call it parallel plate, Conan plate, and rotational viscometry, or mixed. Mixed means two type of this or three type of this thing. So this is the concept of the rotational rheometry. So you are rotating some disc, which is it's in surface with the material, and then you measure some melt parameters like shear rate, shear strain, or shear stress. Now, if you want to go more in theoretical part of the subject, so this is the ideal stress-strain behavior of the fluid. So we are dealing with the angle, we are dealing with the shear stress, we are dealing with displacement, torque, and those parameters that usually are related to rotational viscometry. So as you can see from this figure, this is a linear motion that we're dealing with capillary rheometry. And this is a rotational motion or rotational velocity or angular velocity. And also this is a rotational one. So these two are dynamic polymer melt testing. And this one is idea of they call it capillary or static testing. So you are dealing basically with viscosity, shear stress, shear rate, which is related to torque and force. So those are parameters that we are going to talk about today. This is the main machine, actually, exact machine that we have here, and we are doing the experiment with that machine. So those are parameters are involved. The force or load that we apply, actually this is torque in terms of the rotational. So you are dealing with temperature, frequency, shear rate, shear stress, and deformation. So these are a range of the value that we use for that machine. I mean, that's how come Mars, Thermocentric is a company that made that machine. So we have this machine here in the lab, and you may already saw that machine. So the geometry or sample geometry that we have here is like 20 millimeter diameter and 8 millimeter thickness. So we are going to have this type of geometry, as I said, 20 millimeter diameter and 8 millimeter thickness. So this is a disc actually with this dimension, 20 millimeter diameter and 8 millimeter thickness. This is a standard for most of the, dynamic testing. Okay. As I mentioned from the beginning, these are differences between rotational rheometry and capillary rheometry. This is the main difference. If you look at this graph, the range of the polymer properties that we are measuring in capillary viscometry are different than rotational rheometry. Why? If you look at these two graphs, it clearly shows you that when you are working in the capillary rheometry, so your range of shear rate and viscosity is like 100 based on the shear rate. And here also, when you're dealing with the shear rate for different type of the material, for capillary rheometry, you are dealing with a die. So when you are dealing with the capillary rheometry, you are dealing with the die diameter and die length. But when you are dealing with the rotational rheometry, you are dealing with a thickness and a disc with a thickness and with a diameter. So those are geometry that you are dealing and range of the material property that you are getting. So if somebody asks you, okay, what is the difference between these two viscometry, rotational and capillary? Main difference is range of the shear rate and the other property that you are getting. Of course, when I say shear rate is related to shear stress. Shear rate is related to viscosity. So that means the range of the property that you are getting from different type of the equipment like rotational and capillary are different. That's the main and key difference between these two equipment. So the other difference between these two capillary, capillary and rotational rheometry is in rotational rheometry we are not measuring directly the stress and strain. So we apply the force, we apply the torque, and we get some number, and then based on the number that we are getting, we correlate those numbers to the shear stress and shear strain and shear rate. So this is a concept and equipment, and the idea of the rotational, or sometimes they call it oscillating, the moving rotational equipment on the surface of the material. So we are dealing with temperature, we are dealing with load, torque, and sample geometry. So in general, when you are dealing with rotational viscometry, as I said, we are dealing with the dynamic loading. We are dealing with the rotational. So the base for those flow, I mean that the equipment or load that we applied on the material, on the sample, is some type of the dynamic loading. So in this type of the testing, we apply the load at the surface of the material, and one face is stationary, and the other face is rotating. So by applying the force on the material, so we measure shear strain, we measure shear stress. As I said, they are related to viscosity. Okay. So as I said, there are 4 different type of the setup for rotational rheometry. I will explain one by one in detail. The first one is parallel plate, second Conan plate, and the third one is rotating cylinder viscometry. I'm trying to explain all of these, and the fourth one is actually mixer. That means, you know, the combination of 2 or 3 of this technique. So this is the first one, parallel plate. As name says, parallel plate means your stationary plate and your moving plate are parallel. That's why they call it parallel plate. So your material with the thickness or gap is between 2 parallel plates. So in general, one of the plate is, rotating, and one is stationary, and this is a machine that have been used for viscometry. So this is the simplest viscometer that you have for dynamic testing. So you have a rotational cylinder. So sometimes instead of having a plate, you have a 2 cylinder is inside each other. So one is stationary, another one is rotating, and your material is between 2 cylinders. So this is another concept. They call it rotating cylindrical viscometry. So there are different type of setup that we can have to measure dynamic polymer merge property like shear stress, shear rate, and viscosity. So for parallel plate, this is a very simple geometry that you have. So you have a different diameter. See, this is plate diameter. So it shows you as your diameter, your plate diameter is decreasing, your shear stress is increasing. This is just relation between plate diameter and the parameter that you are measuring, like shear stress. And this is relation between another parameter like shear rate with thickness or gap. So if your gap is decreasing from like 2 millimeter to 0.5 millimeter, then your shear rate is decreasing. Why is that? It's just based on the formula that you have here. If you look at this formula, there is a relation between this formula and the shear stress that you have. So this is shear stress, and this is diameter. You increase, by increasing the denominator, then you are increasing your shear stress. Same thing here. So there is the relation. You already know this topic that if you have a relation with, I mentioned this thing several times, that you have a relation like A proportional to B, or A inversely proportional to B. So this is exactly the concept that you have here. When you say A proportional to B or A is inversely proportional to B, that means exactly the same topic that you have here. So these are not, something that complicated. It's just relation between diameter, shear stress, gap or thickness of your material, and shear rate. So for column plate or for a geometry which is not the straight plate, so they call it, this is plate, or this is plate, and this is cone. So it has angle. So you are dealing with the angle here. So it has different angle, like 2 degree, 1 degree, 0.5 degree, and this is your diameter again. The same concept apply. The changes in shear stress and shear rate regarding the geometry, you have same concept that we have in plate. So for cone geometry or for the cone, viscometry, you have exactly. Okay, let me. Sometimes. Okay. So we have a relation between this geometry and measuring parameter like shear stress, shear rate for both plate diameter and cone and plate. So this is cone and plate geometry, and if you want more, formula, how we calculate this. So we use those formula to calculate viscosity. So M is torque, alpha is angle, and you have some shear torque, as I said, and R is radius of the cone that you have, and angular velocity, and angle, and there is a material constant that they call the K. So in general, for any geometry that you can have plate or cone, both will give you material properties like shear rate, shear stress. What is the difference between these two is dependent on what type of range of the viscosity that we are looking. So this is the machine that we have here. Actually, there is two different concepts for dynamic viscometry. One is a stress control and a strain control. But in general, both do the same thing. For both, we are measuring material properties. So this is another shape of that. Testing equipment that have been used for this type of testing. This is a concentric cylinder, and this is cone and plate, and this is parallel plate. So I think from these three types of equipment and method, if you compare it, each of them are good for some type of property. If somebody asks you what is the difference between these two, this is the main difference between these three types of the geometry. When you are using concentric cylinder, it is good for very low to medium viscosity. When you are using cone and plate geometry, it is good for very low to high viscosity. And when you are using parallel plate, it is good for low viscosity to soft, solid. So it depends to what type of material are you looking and what type of material you want to measure. Based on the material that you are proposed to measure property, you choose your equipment. You choose your geometry. Are you using your parallel plate, cone and plate, or concentric cylinder? So this is actually, again, the same concept. Some of them may be, as I said, there is two different concepts here. They said control strain and control stress. Actually, this part is something related to polymer property too. So when you study viscoelastic material, which is part of the polymer property too, like creep, stress relaxation, You will learn more about the control strain and control stress. But for now, I just want to let you know that there are different modes that we can control the equipment, how we measure it. So this is exactly the same thing as I mentioned. And this is exactly, I mean, the same thing, same concept that I mentioned. If you want to have a graph of the shear rate versus viscosity or shear rate versus shear stress, so this is similar to capillary rheometry. When you present your data in terms of the graph, the same concept that you are using with capillary rheometry here is applying. So, and this is some formulation that I think is more related to lecture. And why, you may ask yourself, okay, why are we interested in dynamic rheology? What is dynamic rheology? What is dynamic testing? The question is, it can measure molecular structure, molecular weight. It can measure, you know, it can have a relation between properties and molecular weight. So you see here for different type of material like low density polyethylene, linear low density, and high density, you will get different modulus, different properties. And the equipment is measuring for you, and it will determine what type of material you have. So this is the concept of the dynamic testing. And there is the last one that I would like to say. This is the last sentence, I think the last slide regarding the polymer melt or dynamic polymer melt testing. We have two concepts here. One is a storage modulus, and one is loose modulus. Actually, as I mentioned in the class, we have viscoelastic material. We are dealing with viscoelastic material. So a storage modulus is actually related to elastic bond. So a storage modulus G dot is related to elastic bond. And G double dot loose modulus is related to viscosity. So this is main difference between G dot and G double dot. As I said, some part of this subject is related to polymer properties too. So when we are dealing with viscoelastic material, we will explain about G dot and G double dot more. Okay, this is the end of this lecture today.
Hello everybody. In this video, we're going to be talking about our rotational rheometer, specifically our hockey MARS rotational rheometers. The MARS stands for Modular Advanced Rheometer System. Advanced rheometer system because it can tell us a lot of things, not just rheometry. It can also tell us about creep relaxation and just creep stress, other things such as G prime, G double prime, and various other factors, and we'll get into that a little later on. Like I said, this is our rotational rheometer. So essentially how it works is we have our two panels right here, and there's another panel up in here, and they're both, in this case, they're both small circular plates. And so we have our material here. In this case, we have a specialty PLA with carbon nanotube infill, according to Skip at least. So it's just these little discs, and these discs can vary in size depending on the kind of test we want to run and what kind of data we're trying to find. So essentially we just take the disc, we put it on there, and we can lower this down, and the plate in here is about the same size as this disc. And essentially, once it applies pressure, what it will do is it will rotate, or rather this one will oscillate, and it will just go back and forth repeatedly over time. This is our monitor setup for the rotational rheometer. Using this program, we can set various tests, and we'll go ahead and go over a few examples. So we can create a creep and recovery test, and in this case, here we have our actions essentially that the machine will undergo. So first, the lift, that top portion from the rheometer, if you guys remember, will move to a 0 point, its standby point, which is in this particular test set at 60 millimeters. And then it will also proceed to its set temperature. This particular one set at 25 degrees Celsius, so about room temperature. Then the lift is going to move to measurement position. So essentially the lift is going to come down to that bottom plate and move to, it's about an inch above it, and it's going to sit there. And then as soon it will start moving ever so slightly closer and begin its creep and recovery test. So in this case, we're doing a constant stress test, and it essentially is trying to apply 600 pascals of force, usually represented by the numeral tau, and then essentially it's going to do that for 60 seconds, and then it's going to let go for 60 seconds, and then it'll give us our creep analysis, and eventually it will lift. And we can go over to our data manager, if I can find, here we go, creep. So here we have the analysis from our test. So this is our creep recovery and creep relaxation test. So we have our increasing gamma, and that's when the test begins, and here is the conduction of the test. And after that 60-second time period, it lets off and allows, and essentially it just continues to test it, and we have our decrease. And here we also have our application of force for the 600 pascals. And this particular machine can conduct various other tests as well, including amplitude and sweep. That looks wild. That also looks wild. Here, this one looks slightly more normal. So here it gives us our G prime and G double prime for your loss and reduction. Also gives our gamma and percentage. And here, right here, we have the beginning of the test and or conduction of the test, and then drop off when it's sort of letting off and continuing to measure. So this video is part 1 of 2. Part 1 obviously being the rotational rheometer. Part 2 we'll discuss the differential scanning calorimeter as well as the thermogravimetric analyzer.